Well, hello, and I would like to now go over an additional lecture on electric current and DC circuits, in particular, more sophisticated electric circuits that we haven't seen before. So I'd like to talk about Kirchhoff's, or some people just say Kirchoff's. There's a lot of pronunciations. I believe he's Danish in his last name. Rules for electric circuits. So, we will have a look at this lecture for more sort of complicated battery and resistor networks. Okay, so let's introduce Kirchhoff's rules. Okay, notice that in circuits with multiple voltage sources on branches, the series and parallel rules alone cannot fully analyze the circuit. Notice that when you have this circuit here, notice that you're not going to be able to just use the traditional series and parallel rules because there's multiple branches, there's multiple currents that are labeled, there's multiple batteries and directions and so on. So, usually multiple currents are the unknowns of a complicated circuit. Usually we know the EMF sources or the batteries and their internal resistances, we can estimate those. And usually we know the load resistors, but we don't know the currents, and we can actually predict them. We need at least as many equations as unknowns to solve that system, and it turns out Kirchhoff's rule number 1 follows the conservation of charge. For charge flow, that is electric current, where electric currents meet. So we're going to look at some rules about these junction points where currents either split up or recombine. And then rule number 2 is going to follow the conservation of energy for electric potential, that's voltage, for a continuous circuit. Okay, so let's have a look at Kirchhoff's circuit rule number 1, which is often called the junction rule. And the junction rule says the following, that the sum of all currents entering a junction equals the current leaving a junction. Now, often textbooks write it this way, in sort of a very physics sophisticated way, which I don't think is very helpful. The sum of all the currents at a junction is 0, as if there's a positive and negative direction to current. I don't think that's very useful. Another way to write this equation is the sum of all the current that goes into a junction is equal to the sum of all the current that goes out of a junction. In other words, conservation of charge, but just for charge motion. That's how I'll write this in class, or at least like in these lectures. So imagine you have a junction like so, where this is a conducting wire, and there's a junction point. If the current that goes in is I1, and the currents that go out are I2 and I3, you can just say that if I1 is, let's say, 11 amperes, and I2 is 7 amperes, then I3 would be 4 amperes, for example. So you could say I1 equals I2 plus I3. And a useful analogy of Kirchhoff's loop rule, rule number 1, is the conservation of flow rate for an incompressible fluid. When current goes into a junction and splits up into different currents, I1 equals I2 plus I3, that's like the flow rate in is equal to the sum of the flow rates that go out. So as long as a fluid is incompressible, conservation of mass is very similar via the continuity equation to conservation of charge, which is, again, for electric current. Now let's have a look at rule number 2, which is the loop rule, which is often stated the sum of changes in electric potential, which we know to be voltage, around any closed circular path, which we call a loop, must be 0. So the sum of all the voltage changes around the loop must be 0. In other words, we account for all the gains and losses of voltage when traversing a loop. So imagine we have this particular example. Suppose we have an EMF source which has an internal resistance, and suppose we have a couple of resistors here, and suppose we want to figure out what the current is. Now, for this particular problem, we can actually just use series circuits, but I want to demonstrate the loop rule for this particular example. So notice that, suppose we start in the upper left-hand corner, as this loop seems to suggest, at the 0 volt point. We cross the EMF, so that's a positive voltage gain. We subtract the resistance multiplied by the current of the internal resistance of the battery. Then we multiply the current times each load resistor and subtract it, because those are voltage losses, and then we must get back to 0. Note the continual use and reuse of Ohm's law, that is V equals IR. This is a voltage equation, whereas the circuit rule 1 was a current equation. In other words, the equation was in terms of amperes. This equation has to have units of volts. Typically, we must choose which loop and which direction. So in general, you have more complicated circuits. Now, sometimes whoever draws the circuit diagram gives you the labeled directions of the currents. So in this case, I1 and I2 and I3 are given to us. Okay? But in many cases, you will have to choose the direction of the electric current. So in that case, you should just choose and label those electric currents in terms of their size, or in terms of their direction, and then calculate from there. Now, when we apply Kirchhoff's rules, here's what we're going to do. We first use the junction rule, and I suggest label the current in each wire section or branch, I1, I2, etc., and pick a direction. Suppose you solve Kirchhoff's rules and you get a negative current. That actually means the current really goes the other way as to how it was labeled. So in that case, you would either need to relabel the diagram, or for that matter, you would need to just note that a minus means opposite as labeled. Now the loop rule says you should choose a direction to traverse a loop, clockwise or counterclockwise, and you should label that on the circuit diagram. Now when a resistor is traversed in the same direction as the current, the change in the potential is delta V equals minus IR. That's traditionally what happens with resistors. Resistors usually take energy away from the positive voltage potential that's available, and so the delta V equals negative IR, as long as we're going in the direction of the current. But if a resistor is traversed in the opposite direction of the labeled current, then the change in potential is plus IR. That's to make sure we get the signs right, S-I-G-N-S, the signs. Now, when a source of EMF, typically a battery, in terms of its ideal piece, is traversed from its negative to its positive terminal, the change in the potential is delta V equals plus the EMF. Notice, in these calculations, I will use the direction of conventional current, namely the Franklin convention. So we assume that typically charges come off the positive terminals of batteries. And when possible, we set the 0 value to the negative terminal of the of a battery. So that's the 0 volt location if possible. But then finally, the last rule. When a source of EMF is traversed from positive to negative using the loop rule, then the change in voltage is minus epsilon. Okay? So notice that if you're going across a battery in the wrong way when you're looping, then you do minus. Now, by the way, with respect to these batteries or voltage sources, the current direction here does not matter. What matters is the direction that you are looping. So here is a pictorial way to show what I just said out loud in words. Notice that if you go across a resistor with the current, it's minus IR. That is VB minus VA, in terms of the delta V. If you go across a resistor from A to B against the current, it's plus IR, VB minus VA for delta V. If you go from A to B across a battery in the correct direction, that is a voltage source, from the negative to the positive terminal, it's plus capital epsilon. But if you go across the battery from A to B in the wrong direction, irrelevant of the current direction, then VB minus VA is minus epsilon for delta V. Now here, I want to give you a couple tactics. So I will talk through some of these briefly, but otherwise you should pause the video and read through all this if you need to. But I would suggest draw a circuit diagram, label all the known and unknown quantities, assign directions to the current, draw and label current arrows to show your choice. The batteries should sort of indicate the direction you think the current wants to go. Now remember, if you get a negative current, the direction is actually opposite what you chose, but that's fine. You can just relabel later. Travel around a loop. Okay? Start at a point that you label, and then delta V is always downstream minus upstream. And again, here's the rules when you go the correct direction across a battery, you go the wrong direction across a battery, you go the correct direction across a resistor, and because I think I just ran out of space in order to make this box not too small, if you travel across a resistor this way against the current, it's plus IR as opposed to minus IR. And always apply this loop law, and always, that's Kirchhoff's rule number 2, and also apply that the sum of the currents at a junction point, all the current going in is all the current going out. Okay, so here's a conceptual example that I'll go through here in the notes. Apply the junction rule to the circuit on the right. Okay, so let's imagine we label current I1 and we label I2 and I3. Okay, I1 seems to be this way because of a battery pumping charge this direction, we think. And then it's hard to tell what I2 and I3 should be in terms of their directions. So let's just call them this way and this way. Okay, so I1 should equal I2 plus I3 as labeled. The incoming current, I1, is equal to I2 and I3 that exit. How about we apply the loop rule to the circuit on the right? Suppose we start here at this dot for both loops. Suppose we call this top loop A, and suppose we let it be clockwise. Well, we're going to go this way, so that's going to be the following equation. So notice that I1, this current, is on all these pieces of wire, and I hope you see that. So it's minus I1 R2, because we go the correct direction across this resistor, plus EMF1, we're going the correct direction across a battery, and then minus I1 times lowercase r1 of the battery, because, well, we're going across the battery's internal resistance, and then we get to this junction point, and then we continue clockwise across this load resistor, but with current I2, so it's minus I2 times R1 equals 0. Okay. So how about bottom loop B? Now bottom loop B is going to be down here, and it's also going to be clockwise. Now notice bottom loop B, let's start here, and now let's go the other direction across R1. So it's exactly the opposite of this term we had in the previous equation. It's going to be plus I2 R1 because we're going against the current across resistor R1. Then we get to this junction point. Now we're with current I3 the rest of the time to this starting point. So we go across R3 with the current I3, so that's minus I3 R3. We go with the current across the battery's internal resistance, so minus I3 R2 of the battery, of the second battery. And then notice that now we go the wrong direction across this EMF source, so it's minus EMF2 equals 0, because we get back to this point. Now, by the way, people have often asked me many questions about this, so let me try to clarify those from the get-go. Can you start in any corner or in any place of this circuit? Sure you can, okay? As long as you're careful. Secondly, you can't really start in the middle of a resistor or the middle of a battery. You probably should start on a piece of wire where everything on that piece of wire is at the same potential, at the same voltage. So that way you're consistent. Next question, what if loop A would have been the exact same loop, the exact same starting point, but you'd have gone counterclockwise. Well, if you had gone counterclockwise, it'd be plus I1R2 minus EMF1 plus I1R1 battery plus I2R1 equals 0. In other words, the entire equation would have just been the opposite. In other words, you'd have just multiplied the loop equation by -1. But multiplying a loop equation by -1 just means you're going in the opposite direction. And let's see, one more thing is, people have often asked me, can you do the entire outer loop as opposed to these inner loops? And again, sure you can. Now, by the way, there's many ways to construct loops here, but you only really need to do as many loops along with a junction equation that gives you enough equations to solve for the unknowns. Now, in this case, I think the unknowns are I1, I2, and I3, the currents. Suppose we know what the resistances and the voltages of the batteries are. So we need one junction equation and two loops. Okay? If you did a third loop, it would be sort of redundant. But again, some people want to get many equations, but I think it makes extra effort. Okay, I will perform this example in a later problems video. So this is an important example to kind of get you going in terms of calculating currents, namely I1, I2, and I3 in this circuit. Okay, and this is probably the hardest example that I will do. I will do this in a separate, again, problem video. By the way, when these circuits get quite complicated, you have multiple batteries, multiple resistors, multiple currents, and to solve those many linear equations would take a lot of effort. I recommend using a linear solver. So the linear solver that I will show in a later example video is going to be a matrix solver. I will show how to solve a 3 by 4, 3 rows, 4 column matrix. The fourth column is actually the solution, namely the augment. And then what we'll do is we'll get the values of the currents by solving the equations simultaneously. Okay, so I want to thank you for your attention in this lecture video. Please smash that like button if you like this content and share it with people that are in your sphere of influence. I ask you to subscribe to this channel if you like the content, and please support the channel in those following ways. I will see you in the next video, and thank you for watching.